All right, we are going to move on to chapter 8, which is called sampling distributions. So we are, I believe, just doing two sections here, 8.1 and 8.2. And let's get started. The first thing we're going to do is we are going to find distributions about the sample mean. We will first start with a normal population and then show what happens if we have a non-normal population. Statistics such as X bar, meaning the sample mean, are random variables since their values vary from sample to sample. So if I were to sample 10 people and take their average height, that is going to be slightly different than if I take a different 10 people and get their average height. Okay, so that's what they mean by it's a random variable. It varies from sample to sample. So as such, they have probability distributions associated with them. So what we're going to do is we're going to look at the shape of them, the center, and the spread of things such as the sample mean, as well as proportions. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from the sample size n. The sampling distribution of the sample mean, X bar, is the probability distribution of all possible values of the random variable, X bar, computed from a sample size n from a population with mean, mu, and standard deviation, sigma. What's going to happen? We know our population mean and standard deviation. We are going to be told we're going to take a sample of size whatever, and we want to create the sampling distribution of those averages. Okay, that is what we are going to create today. So here's the idea behind it. We're going to obtain those simple random samples of size n. We're going to work through the process here to show you what happens. We'll calculate the sample mean. And then, assuming that this is finite, we can repeat this so many times until we've gotten our random samples. So just to note that if we take a certain random sample, we cannot ever use that same exact group of random sample again. Let's work through a process here. An intelligent quotient, the IQ, is a measurement of intelligence derived from a standardized test, such as the Stanford-Binet IQ test. Scores on this test are approximately normal with a mean score of 100 and a standard deviation of 15. Pretty sure we've worked with this IQ before. We're going to work with it again. What is the sampling distribution of the sample mean for a sample of size 9? All right, so here's what we're going to do. We're going to run through on the next slide here is going to show random samples that were created from the overall population. Each row is going to represent a certain that number sample. Then in the last column is going to be the average of that sample size. Looking here, sample 1 has these 9 values. And then the mean is calculated here. All right, so what we're doing is these 9 values were taken from the population, and we calculate the averages over here. The averages is going to be our new graph. This is what we're going to graph to create our sampling distribution of the mean using sample size 9. Okay, so sample size 9 means there's 9 in my sample, and I repeat that process however many times. A is the population distribution. So the mean is 100. The first standard deviation is 115. The next standard deviation is 130, and then the third standard deviation will be out there. The second one here is the histogram of our sample means. So we took only these values, all of our sample means, and graphed that data. And what it's going to do is it created its own bell-shaped curve. And look at this. The mean is still 100. All right, so this one had a mean of 100, a standard deviation 15. Over here, our samples that we drew still have a mean of 100. 100 occurs the most frequently. And that should make logical sense. If 100 is the most common here, it's going to be picked the most frequently in our samples, and our average is going to be close to 100. Okay, that is why that stays the same. Now, standard deviation, though, is 5.014. So our standard deviation changed. And just so you know, this N down here means that they took 9 samples 1,000 times. So far, my normal population created an approximately normal graph. My mean stayed the same, and my standard deviation changed. Okay, that's all we know so far. We notice the center of the distribution is the same as the center of the population, but the spread of the distribution is smaller than the spread of the population. In fact, the mean of 1,000 samples was 100.2, which is close to the population of 100. The standard deviation was 5.01, which was less than the population of 15. Here's what we can conclude. The shape of a distribution of sample means is approximately normal. The mean of the distribution of the sample mean equals the mean of the population, which is 100. And the third, the standard deviation of the sample mean is less than the standard deviation of the population. So anytime you are going to be asked to describe the sampling distribution, you need to talk about all 3 of these things. All 3 are required to explain or describe the sampling distribution. So what we're going to do now is we're going to repeat that problem, but instead of using a sample of size 9, I'm going to use a sample of 25, and we're going to see what happens. Here's our histogram. You note that 100 is still right in the middle here. And in this case, it is still, the mean is still 100. But my standard deviation got even smaller. The figure on the previous slide shows the histogram of the sample means of size 25. Notice again that the sample means appear to be approximately normal, number 1, with the center at 100, number 2, and less dispersion than the original histogram with our new standard deviation of 3.08. So those are all the 3 things that we have. So the distribution of mean with sample size of 25 has less variability than the sample of size 9. What does that mean? It means it's less spread out. So the more that are in my sample size, the closer my averages are going to be to each other, meaning my standard deviation is going to be smaller. What role does N, the sample size, play in the standard deviation of the distribution of the sample mean? As the size of the sample increases, the standard deviation of the distribution is going to decrease. So the larger I make my sample size, the less spread I am going to have. There has to be a formula. There has to be a true relationship that's happening here. There is. Okay, so anytime we have a simple random sample that we're going to take of size whatever is drawn from a population and we're given our population mean and standard deviation. Okay, the mean of the sample equals the mean of the population. So sample mean equals population mean. That's part 2 of what we said. Part 3, the standard deviation can be calculated as follows. Sample standard deviation is equal to the population standard deviation divided by the square root of your sample size. So if we are just told these three pieces, I want to take random samples of size 10 and a mean and a standard deviation, I can write what my mean will be, and I can write what my standard deviation for that sample distribution will also be. I can calculate those. Standard deviation of the sampling distribution is also called the standard error. So as long as you have drawn from an approximately normal distribution, the sampling distribution will also be approximately normal. And that was the first thing that we discussed. So we're going to work through an example here next about how we go through all of this. So just to show you here, the IQ scores of individuals are modeled by the random variable. The blue is our overall population. The mean was 100, and our standard deviation was clearly much more spread out of 15. And the first one we did a sample of size 9. So what happened is it is still normal, but you can see here that the graph shape changes. Okay, it's a lot more narrow and it's a lot taller. The mean stayed the same at 100, but the standard deviation turned into 15 divided by the square root of 9. And if you don't believe me, we can do that really quick here. I can take 15 divided by the square root of 9, and I get 5. So if I were to go back here, 5.01 is what was calculated in the graph. So we had a really good estimate there of 5 with the formula. Just really quick here. I'm going to do another example before we move into the problem that's after this. A simple random sample of size 25 is taken from a population with mean equal to 80 and a standard deviation equal to 10. Describe the sampling distribution. Okay, if it is coming from a population that gives me a mean and a standard deviation, it is also going to follow that it has a mean and standard deviation. It's going to be approximately normal. So approximately normal is the first thing that I am going to state. Step 2 is going to be mean of the sample. Mean of the population is 80, and the mean of the sample, so mu of x bar, is also 80. Okay, so that is the second thing that you are going to write. The third thing you're going to do is calculate the standard deviation of the sample, which takes the population standard deviation of 10, dividing by the square root of 25. Square root of 25 is 5. So 10 divided by 5 is 2. So that is how you would start any of these problems when it asks you to work with a sampling distribution. All three of these things are required to be listed. Another way that you may see textbooks, or if you're looking at other resources online, you could write it like this: approximately normal with the distribution n 80, 2. So n stands for normal, 80 is the mean, standard deviation is here. That is another way that books and other websites will write it, however you want to write it, either listing all three things like this or like this. I need to see all three of those pieces. Once we calculate that information, we can then ask questions about probabilities. So the IQ of humans is approximately normal with a mean of 100 and a standard deviation of 15. Compute the probability that a simple random sample of size 10 results in a sample mean greater than 110. That is, compute the probability that the sample means is greater than 110. The first thing we start with is our sample mean will be normally distributed. Step 1, the mean of the sample. Step 2 is still 100. Step 3, calculate our standard deviation by taking the population standard deviation of 15 and dividing by the square root of 10. We're going to get a decimal. These decimals are going to be long decimals. The more that you save decimal-wise, the more accurate it's going to be when you plug it into StatCrunch. Just know you don't want to round to just one decimal place. You want to keep a few decimals for these guys. Other things you want to check is the sample size less than 5% of the population size. Okay, a sample of 10 dealing with the entire United States population clearly is not more than 5% of the population. And then we're going to have a normal curve. What we're going to do is we're going to then go to StatCrunch to calculate this. So our mean is 100. We want to find greater than 110. And we're going to use that process that we used last chapter in going to the normal calculator, typing in my mean and standard deviation, and it's going to give me my probability. Using our technology here, I'm just going to show you guys really quick. Stat, calculator, normal, and we are going to use our sample mean and sample standard deviation. So 100 and the standard deviation 4.743. 4.743. Okay, we want to be greater than 110. Click compute, and I like to have my 68, 95, and 99.7 marks there. All right, so here's my area, 0.017. That's going to round to a 5. And you'll see that should be the same. Well, they have 4. Okay, so I have 5 just because mine rounded. Using technology, there's a 5 there. All right, so what does that mean? The probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 and approximately 0.02 is approximately 0.02. So we are talking about the probability of obtaining a sample mean to be greater than 110 is, and you could do this value here, 0.0175 is this. You don't have to round to 2 places. What that means in general is if we were to do this 100 times of sample size 10, we would have about 2 of the time, about 2 of those samples would have an average mean greater than 110. The distance traditional home runs traveled in 2017 is approximately normally distributed with a mean of 400.3 feet and a standard deviation of 25.6 feet. Suppose a sample of size 16 is taken. Describe the sampling distribution. Okay, so anytime we describe a sampling distribution, we will say it is approximately normal. We will list our mean of the sample is going to be equivalent to our given mean, 400.3. And then we're going to calculate the standard deviation of our sample by taking the 25.6 and dividing by the square root of 16. The square root of 16 is 4, so 25.6, we're going to divide by 4, and you'll get 6.4. So this one rounded nicely. Next one is find the probability that X bar, so my sample mean, is greater than 405. So the second part here, find the probability that my sample mean is greater than 405. I'm going to pull back up my StatCrunch. 400.3. Standard deviation 6.4, and we want it greater than, I think it's at 405. So this one here, anytime we write these values, we go to 4 places. So 2, 3, 1, 3, that 6 is going to round that up. So 2, 3, 1, 4. So about 23% of the time, our sample distribution is going to have an average greater than 405 feet. The probability that my sampling mean is greater than 405 using my sample size 16 is going to be about 0.2314. All right, so next one here asks about these symbols. So the probability that X bar is greater than 405 is different from the probability that X is greater than 405. What is the difference? Okay, X bar greater than 405 is the sampling mean. So this has to be done when you take a sample, from the population. If it is just X, this is population value. This is what we did back in chapter 7. We were just told, hey, I have a mean, a standard deviation. What's the probability I get a certain value? That's this one in chapter 7. What we're doing today now is taking samples from that population over here, averaging those samples and getting a new distribution. And that is this distribution here, X bar. So please, please, please be careful when you're looking at those symbols to make sure you're doing the correct one. All right, so next one. A simple random sample of 49 is obtained from a population with a mean of 80 and a standard deviation of 14. Describe the sampling distribution. Well, we always start with it will be approximately normal. Let's list our mean of the sample, which is the original mean, 80. And we got to calculate the standard deviation of our sample by taking my population standard deviation divided by the square root of the sample size. My population standard deviation was 14. I'm going to divide by the square root of 49. 49 is perfect square, which makes 7. Oops. So 14 divided by 7 is 2 for my standard deviation. All right, so all these other problems here say the probability that my sample mean. So I am using these new values in StatCrunch. I have to use these for my probabilities. So let me open up StatCrunch here. And for my mean of 80, by standard deviation of 2. And the first thing we want to do is find that the means are greater than 83. So I have 0.0668. There's a 0 after it, so we're good there. 0.668. All right, so the next one is the probability that the sample mean is less than 75.8. I'll go back to StatCrunch. I'm going to change my symbol and my number. So 75.8, oops, 0.8, but I want a less than symbol. Okay, so 4 numbers, 1, 2, 3, 4. That 6 is going to round that 8 up. So 0179. And again, this should look really familiar to what we were just doing in chapter 7. The only difference is you have to do this first step of describing my sample distribution first. The last one then is a between 78.3 and 85.1. 78.3 and 85.1. what did we say? 85.1. All right. So graphs it, shades it for us. So 1, 2, 3, 4. It's gonna round my 9 up. So let's see, 69 rounded is 70. So 7970 is gonna be my answer. Second thing we're gonna look at then is what happens if my original population is not normal. Okay, can we still do these calculations if my original population is not normal? All right, so let's take a look here. The data in table 1 represents the probability distribution of the number of people living in a household in the United States. And the next slide is going to show the graph. It looks like here the most common number of people living in a house is 2. And we've got all the way up to 10 here. So my graph, if I were to graph this, is very skewed to the right. This graph was created, and back here gave us an average of 2.9 and a standard deviation of 1.48. Okay, and clearly by looking at the visual of it, it is not normal. Also for the fact that you can't have fractions of people graphed here, so it's not a histogram. It has to be, these are solid numbers, not continuous values. They're discrete. But let's see what happens here. Let's pretend or go through the example. We're going to make 1,000 samples of size 4, of size 10, and size 30. And what's going to happen is I'll get 4 values. I will average them together. I'm going to repeat that 1,000 times. Then I'm going to take samples of size 10. So I'm going to pick 10 samples, 10 pieces from the data, average them, and repeat that 1,000 times. I'm going to do that one more time, taking samples of size 30, finding their average, and then graphing their averages. The next slide is going to show what happens for sample size 4. And columns 1 and 2 represent the probability distribution. And each row in column 3 through 6 lists the numbers of the individuals that were chosen. Column 7 is then mean, sample mean for the row. Just looking at it here. This was our original data. So that was our data. Here's our sample. Individual 1, individual 2, individual 3, individual 4. So 4 values averaged together. Here's our mean of the sample. Okay, so then I do it again. I pick 4 values, calculate the mean. I pick another 4 values, calculate the mean. Another 4 randomly chosen, get the mean. Randomly chosen, get the mean. This is repeated 1,000 times. And then these values are graphed. Let's see what happens. We have a mean, 2.9, a standard deviation, 0.7616. And you can see here, it looks a little better, but we still have some skew here. Okay, it's still skewed right, but it's not as skewed to the right. So just increasing from, rather than looking at individuals, going up to sample size 4, made it slightly better of a graph. It may not be exactly normal yet, but let's see what happens as we keep working. This graph is what happens if we take samples of size 10. The same thing, 10 values, average them. Get another 10 values, average them. 10 values, average them. And we're graphing all those averages here. All right, so again, we still have, it still is a little skewed right. But again, we're getting closer and closer. You should see here, look at the difference. This one went all the way to 7. So the original graph went to 10. This graph skews to 7. This one only goes to 5. So we're getting, the data is getting closer together here. It's still not normal, but we're getting there. And my mean is still just about 2.9 if I rounded. My standard deviation did get a little smaller. That should make sense though. As I increase my number in my sample, my standard deviation will go down. Last one here. What happens when we've now picked 30? Once I pick a sample size of 30, my sample mean now looks approximately normal. This looks like a normal bell curve. It looks symmetric on both sides. Okay, on our sample mean, if I still round to 1 decimal place, is 2.9. All right, my standard deviation continued to get smaller because my sample size got larger. And anytime you divide by a larger number, your answer is going to be smaller. What is happening here? The mean of the sampling distribution of the samples was still equal to the population. That did not change. That concept is still happening here. The mean of the sample equals the mean of the population. The standard deviation of the sample can still be calculated as the population standard deviation divided by the square root of the sample size. Okay, it doesn't matter what size sample you work with, that formula still works. The shape of the distribution of the sample size becomes approximately normal as your sample size increases. So it didn't matter that this data was originally skewed to the right. It doesn't matter. When I take enough sample, a large enough sample size, the graph turns normal. Why? Well, we're going back to that central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of the mean becomes approximately normal as the sample size increases. According to our textbook here, if your graph is not normal, we need to take a sample size of 30 or more. The sample size has to be greater than or equal to 30 in order to say it is going to be approximately normal. Two choices. They tell me the original population is approximately normal. If they tell me it is already normal with a mean and a standard deviation, I can assume my sample will be approximately normal. If they do not tell me that, or they tell me that it's skewed to begin with, or even uniform to begin with, will turn into a normal graph as long as my sample size is 30 or more. How large does the sample size need to be before we can say the sampling distribution of the mean is approximately normal? The answer always is going to depend on the shape of the distribution we're working with. Clearly, if it was really skewed, the sample needs to, of course, be higher versus lower. But again, we're going to use the general rule of thumb for our textbook of sample size 30. We got almost there. I think we did a sample size of 25 on that one. Worked. The thing is, we're not going to calculate all of these by hand. You're not going to sit here and calculate all these random samples and find their means. So we are just going to go with the standard of sample should be 30. Just to look here, another example, very skewed right. Sample size 4, sample size 10, sample size 25. 25 got us to that approximately normal. It's still not exact though, because this tail is still a little longer than this side. So it would make sense to really say, hey, I want to get to that 30 because that's going to make it really symmetric. So in some cases, it may be slightly lower, but we are going to go with the standard. Let's use 30. If the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal provided the sample size is greater than or equal to 30. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed to the right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? Okay, so first off, we got to go through a few things here. We have our mean, our standard deviation, and we are originally skewed right. So mean, standard deviation, skewed right. Here's my sample, and this is my sample mean. Sample is a random sample, and what I always want you to check is our sample smaller than 5% of the entire population? So what they did here, it seems reasonable that at least 700 low-income pregnant women would be in the entire population here. So yes, our sample size would work. And then we're going to go to our probability here. The reason we can go to the probability is because our sample is 35, which is greater than 30. So we can say we will be approximately normal. Approximately normal with a mean of 30 and a standard deviation. We're going to take 12.9 divided by the square root of 35. And just open your calculator. 12.9 divided by the square root of 35 gives me about 2.1805. Now we want to find the probability that we got greater than 36.2 for our average. So we're not going to do it by hand. We are going to use our curve here. So it was 30 pounds with a standard deviation. Our calculated standard deviation was 2.1805. And we want to see greater than 36.2. 36.2. All right, so we're going to go to 4 decimal places. 0022. The probability that our mean is less than 36.2 is 0022. And I believe that's the same value that we're going to get here. There's rounds to 0023. Ours was 0022. I promise it'll be okay. There's always a little bit of leeway when you enter these answers. Using technology, the way I just did it, we got 0022. This was done by hand. Anytime you go by hand, it may be slightly different. Okay, that's why. So it's asking though, is it unusual? Well, what do we remember about unusual? Unusual is smaller than 0.05. So, is our result unusual? Yes, this is unusual. It is very, very small. The average that I got is not a common average for this population. What does it mean? If the population from which this sample is drawn has an average of 30-pound weight gain, the probability that in a random sample of 35 with a sample mean of 36.2 pounds or more would be approximately 0.002. 0.002 is 2 1,000ths. That means 2 out of every 1,000 would be that average. That is not common at all. That is unusual. The mean weight gain for low-income patients is 30 pounds on average. We just happened to pick a random sample that was not common. What happened here is, looks like those low-income patients seem to have more than 30-pound weight gain. We would have to look into other factors here. Is the diet different for low-income patients? Is their lifestyle different? Did those things impact their weight gain? So lots of times these results can lead us to look into other things here. The shape of the distribution of the time spent in a drive-through at a fast food chain is skewed to the right. The mean time spent in the drive-through is known to be 152.5 seconds, with a standard deviation of 30.8 seconds. The quality control manager wishes to use a new delivery system designed to get cars through the drive-through system faster. A random sample of 50 cars results in a sample mean spent at the window is 148.7 seconds. Why is the sampling distribution going to be approximately normal? We were told we were skewed right. So anytime we are skewed to the right, our sample size has to be greater than 30, which it is. So sample is 50, which is greater than 30. What is the probability of obtaining a sample mean of 148.7 seconds or less, assuming that we come from the original population? We now have our approximately normal population. Our mean is 152.5. And we need to calculate our standard deviation. 30.8 is going to be divided by the square root of 50. 30.8 divided by the square root of 50 is going to give me a standard deviation of 4.3558. Now we need to find that probability of the sample mean. We want to be smaller than 148.7. That's what they're asking me for. 152.5. Standard deviation 4.3558. And we want less than, it was 148.7. 148.7. 4 places, 19149 is going to round that up. 1915. To get a sample mean smaller than 148.7 seconds, we get that on average about 19% of the time. So about 19% of the time, we would have an average of 148.7 seconds. So let's think about this here. Do we think this is effective? Well, my normal average using the entire population is 152.5 seconds. And I've now done a new system. And what happened now, I got about, I have the same mean, smaller standard deviation, but the likelihood that I get less than 148.7 seconds is 19%, okay. But is it really that much faster than 152 seconds? Is there really a big difference here? To go from 152 seconds to 148 seconds. I'm saving the customer 4 seconds. Is 4 seconds going to be very long for a person? Probably not. Did it maybe make it a little faster? In average, not really. Is there maybe a little less spread? Okay, maybe a little less spread. But is it really that effective? Does it make a huge difference? Not a whole lot. I saved 4 seconds, so probably not a whole ton. Okay, this is not unusual. I saved 4 seconds. It's probably not very effective. If your population is normal, normal mean, normal standard deviation, regardless of the sample size, we will be approximately normal. Here's how we find our mean. Here's how we find our standard deviation. If our sample size is not normal, we need a sample size greater than or equal to 30, and my formulas will still be the same. I know It's kind of a lot to work with. We've got an added piece of step here before we go back to what we did in chapter 7. But hopefully this really just works on what you've already learned in chapter 7. You get a lot more comfortable with StatCrunch. As always, if you have any questions, please email me. If you need another example of one of these problems, please just reach out. I'm more than happy to create a quick little video for you. I will see you guys in video 8.